This assessment asks us to synthesize the molecule on the left using a synthesis that involves the molecules shown on the right. Now, luckily, the assessment gives us a hint that we're going to use a Claisen reaction and an enamine reaction. So it gives us an idea of, we know we're starting over here, we're finishing over here, and it's kind of given us a hint to the path. If we didn't have that hint, this would be a much harder problem, but we know we need to use a Claisen and an enamine reaction. Let's start by numbering the carbons, and I've numbered them, and I did it a little bit differently this time. Sometimes I will number the product carbons first. I numbered these first this time, and by doing that, 1 through 5 and 6, 7, and 8, it made it much easier to transfer these numbers and also reveal something to us that will be helpful later on. First of all, if the phenyl group is 8 and it's attached to a CH2 that is 7 and a carbon that is 6, we can put 8, 7, and 6 here. That tells us then that we're going to need to make a bond between carbon 2 and carbon 6. And so we would think about, how can we make carbon 2 a nucleophile? Well, that carbon 2 is right next to a ketone. The enamine synthesis will allow us to do that. Putting in the other numbers, 1, 2, 3, 4, and 5, that's pretty straightforward for the left side of the molecule, 1, 2, 3, 4, and 5. But what about the others? Well, notice we have 2 methyl groups attached to the same carbon, just like we have over here, 5, 3, and 4. So we can do 5, 3, and 4. 3 was attached over here to carbon 2. 3 is attached to carbon 2. And we would expect carbon 2 to be attached to another carbon 1, right? We've got 1 through 5 on the left side. Where's the 1 for this portion of the molecule? Well, it probably fell off, and because it was a it's an ester here, that kind of gets us thinking about, well, maybe at some point it's a carboxylic acid, and so it can do a decarboxylation. So again, the numbering of the carbons gives us enough of a hint that, coupled with the fact that we're going to do an enamine reaction and a Claisen reaction, we probably can get where we're going. All right, so working backwards, let's do the enamine reaction first, because we're going to make the carbon 2,6 bond next to a ketone. And so the way we'll do that, let's just draw the ketone that we would start with. And we can put in our numbers, so 5, 4, 3, 2, 1, 2, 3, 4, 5. This ketone, if we want to do an enamine synthesis, we would start by making the enamine. We can use any secondary amine. We'll use this one. Step 1 would be that. Step 2, the enamine that would result from this reaction, we can react with an acid chloride, and that's going to allow us to keep the ketone present. So if we react it with this acid chloride, that would be carbon 6, carbon 7, and carbon 8. And then we work up the reaction with water, as we always do in the enamine synthesis. That restores this carbonyl. So we're not showing a mechanism here, but the amine reacts with the ketone to make an enamine, which is nucleophilic at carbon 2. That reacts with the strong electrophile, carbon 6, and then we hydrolyze the resulting iminium to give us the final product. Now, a couple of things come out of this, and we can look and say, okay, well, how are we going to make this 6, 7, and 8? Let's jump over to how we would do this, starting with the primary alcohol. So we can react this primary alcohol. We need to convert it into a carboxylic acid. We can do that in a couple of different ways. The common way you might think about doing it is to add chromic acid and water, and that should oxidize it all the way up to the carboxylic acid. Now we know that chromic acid is a pretty toxic reagent, so we would want to avoid doing that. The other way we could do it, if we wanted to avoid the use of chromic acid, one way, and there are multiple ways to oxidize primary alcohols to aldehydes, but one way we might do that is to use the Sworn oxidation, where we react DMSO, oxalochloride, and triethylamine. In a particular order, we're not going to specify the order of addition of reagents here, but the Sworn oxidation would make an aldehyde, and then that aldehyde can be oxidized further using the Pennick oxidation using these reagents. And that would allow us to get to the carboxylic acid and avoid the use of toxic chromium. Now that makes the carboxylic acid. We have to convert it into an acid chloride. So how can we do that? If you want to convert a carboxylic acid into an acid chloride, we react it with thionyl chloride. Let's keep our numbers, 8, 7, and 6. This acid chloride that we need can be derived from this primary alcohol using this synthesis. At this point, we turn our attention to how we synthesize this ketone. And probably this is the most challenging aspect, and where we really need that information that the assessment gave us, that we needed to use a Claisen. Okay, so the Claisen reaction is going to be the condensation of two esters to make a beta keto ester. We need to make a ketone. So how could we do a Claisen and end up with a ketone? To do that, let's take this molecule that is the ester and do the Claisen reaction, see what that gives us. So we're going to come over here, redraw that same molecule, and we'll just do a Claisen reaction as a way of figuring out how we might ultimately get to here. So the first thing we're going to do is we're going to treat this with sodium ethoxide and ethanol. Remember that in the Claisen, we're technically going to have two molecules of the ester. When those come together, the product we're going to make, so we're going to make an enolate on one that's going to react with the ester of the other. The product we'll end up with will be this. So the enolate at this carbon reacts with the carbonyl of another one. That is the Claisen reaction. The Claisen reaction requires sodium ethoxide and ethanol, and then we have to follow that up by an acid quench. But the resulting product is going to be this beta keto ester. Putting in our carbon numbers is going to kind of show us what must happen next. So 5, 4, 3, 2, 1. This is carbon 2, 3, 4, 5. This one would be carbon 1, but carbon 1 is missing from the right side of the molecule. How can we get that ester to just go away? Well, that's going to be the decarboxylation. And that decarboxylation sequence is going to be to take that ester. We can do it in a couple of different ways. We'll show it as saponification of that ester. If we saponify that ester, we'll have a carboxylate. We need to then protonate it, so we can do an acid quench to make it a carboxylic acid. And if this is a carboxylic acid, we now have a beta keto acid. Beta keto acids thermally decarboxylate, so we can heat this. They'll thermally decarboxylate to give an enol first, which we'll tautomerize to this ketone. This ketone can now do the Stork enamine synthesis to make the molecule here. This completes the synthesis of the molecule on the left, making use of the molecules on the right while doing an enamine and a Claisen reaction.